Hello, everyone. I'm Hong Yipan from the University of Illinois, Chicago. Today, please allow me to introduce our ICASSP paper, Real-Time Wireless ECG-Derived Respiration Rate Estimation using an autoencoder with a DCT layer. Here's the background of this work. We want to design an ECG-based respiration rate estimation method for the wireless wearable monitoring system to monitor the health situation. So we have a wearable system like this, which can transmit the ECG signal to the server. So you can see that the ECG signal will look like this, which is shown in the red. And from this peak's magnitude, we can observe is this blue waveform, which can represent for the respiration rate. So usually people will breathe in 15 to 25 times per minute. So you can see that this two peaks interval it matches this duration. Therefore, if we take the DFT on the ECG signal, which was showing in the red, we can compute the respiration rate. So here's the spectrum of our 1 minute respiration, of 1 minute ECG signal. So from this spectrum, we can see that the highest peak in the first part is at 19, which matches the true respiration rate, which is 19.1549. And here's another example, which is the first highest peak is located at 23, and the true rate is 23.42. So we can estimate the respiration rate in this way. And this highest peak represents for the this represents for the heart rate, but we don't use it in this work because the heart rate can be obtained more easily using the ECG-based device. However, sometimes the measurements may be not accurate. This is because we have noise or other that not properly measurement. So for example, in this case, the true rate is 20 BPM, and we have the two peaks. One is at 17, one peak, and another is at 21. And here's another case. The true rate is 70.9, but you can see that the value at 20 is higher than at 18. So in this work, we want to design a neural network-based method to reconstruct spectrum. The reconstructed spectrum should only have a single peak. So here's the proposed method using the autoencoder with a DCT layer. First, we design an autoencoder network, which shown here with six linear layers. The input of the network will be the first 32 entries of DFT spectrum, and the output will be the pseudo spectrum, which will use the Gaussian plot for the training. So in detail, for each training sample, we generated a Gaussian plot whose mean is at the true rate. So the output of the network is also in 32 lengths. Furthermore, we add an DCT-based layer after the autoencoder to improve the performance of the autoencoder. And the input-output of this DCT layer is are also 32. So how do we implement it? We apply the DCT to convert the signal into the frequency domain. Then we apply the element-wise scaling, which we apply the weights on the DCT coefficients. And after that, we apply soft transcoding on the DCT this DCT coefficients to remove the noise, to remove the small noise in the frequency domain. And after that, we apply the inverse DCT to convert signal back. So here's the definition of the soft transcoding. This function is widely used in the wavelet denoising. It removes small noises in the transform domain. And here, we don't usually do because for the nonlinearity, because both the positive and negative frequency components are equivalently important in the transform domain. If we use ReLU, then the negative part will be removed. and we cannot get the perfect reconstruction. So here's the experimental parts of this work. So you can see that from the Dutch curves, it is the first 32 inches of the DFT spectrum, and our AE, which is autoencoder, and AE with DCT, which is autoencoder plus the DCT layer, can reconstruct the spectrum in a single pseudo Gaussian plot. So this one is more clear. So you can see that we get a very good reconstruction. In this work, we have collected about 300 ECG measurements ourselves using the device using our device, and each measurement is 60 seconds, with sampling rate is 500 Hz. We separated this set into 167 training plus 100 testing. And we repeat the experiment because we apply random split here. So we repeat it 3 times to get a better comparison. And we evaluated model based on the MSE and MAE, which are between the estimated rate and the true respiration rate. So estimated rate is the peak location of the generated pseudo spectrums. So from the table shown here, you can see that with the autoencoder, we reduce the MSE and MAE. So these values are much smaller than the traditional Fourier transform based methods. And after we apply the DCT layer, these values are reduced further. So this is our work. This is our work. In this paper, we propose a novel real-time respiration rate estimation method from the ECG data obtained using an autoencoder with a DCT layer. The traditional DFT only based respiration rate estimation methods may lead to inaccurate results. However, the autoencoder with a DCT layer can learn from training data and generate a pseudo frequency spectrum with a single peak. We experimentally observed that the accuracy of the respiration rate detector can be improved significantly using an autoencoder. And we introduced an autoencoder structure with a DCT layer with trainable parameters in the DCT domain. The DCT layer further improves the results of the regular autoencoder. So that is all for this work. If you have any question, you can email me. Thank you.